Hi guys, we're going to be doing tan functions today, so we're going to be sketching tan graphs. This is definitely going to be a bit intense, and it's going to involve using our knowledge to find for solving to find x-intercepts, and also addressing like the shape of the tan graph. So these examples are from 2.6 in your Jacplus textbook. Let's get started. So look, before I address 2 tan 3x, I'll just show you the normal tan graph. So y equals tan x is just like this. It's got asymptotes and it goes like this. So it has a x-intercept of 0, so the origin there, and then what we know about tan is that the period is pi. So remember how in the unit circle we talked quite extensively about how tan repeats. So we'll just say that's pi on 6 and this is pi on 6. Then tan will repeat after pi. So that means that our cycle takes pi, not 2 pi. So when we're doing cos and sine, we're looking at 2 pi where it repeats, but for tan we're pi. So that's why we say the period of tan is pi. So look, the point being that these asymptotes then, if there's an interval of pi between them, this first asymptote is x equals pi on 2, and the second one, or the one in the negative zone, is x equals negative pi on 2. Because from negative pi on 2 to pi on 2, that's a space of pi. So that would be our usual tan graph, our parent graph, if you like. If we then want to deal with the amplitude, it's not really relevant for us. We don't need to worry. We've got asymptotes, so we can just leave it as it is, and I can just call this 2 tan x. What does make a difference is the period, and the 3. This 3 value will change the period here. So if we've got a 3x, that means the period of this one is going to be pi, not 2 pi, divided by whatever's in front of the x, and that's a 3. So that means that I'm going to change this, and my space between these two lines here, these two asymptotes, now has to be pi on 3. So the period refers to how far it is on the x-axis that the graph repeats itself. So now, if I draw that back in, and then we can see that to share pi on 3 across each side, well, it's going to be pi on 6 and negative pi on 6. So it's x equals pi on 6 here, and x equals neg pi on 6. So they would be the asymptotes there. And look, there are formulas for finding asymptotes and x-intercepts from tan. I don't like to use them. I like to really understand, to show the understanding of how we're getting these. So I'm going to do it like that. If you like to use some sort of memorization technique, that's fine, but I would recommend the understanding always first. So now what I've drawn here is y equals 2 tan 3x, and I've just done like one cycle of that. I now can look at the domain from 0 to pi, and I'm going to consider that and extend my graph. So my domain 0 to pi. So that means, well, let's extend this way, because at the moment we've gone to x equals pi on 6. Now we know that the period is pi on 3. So if I times the top and bottom by 2, I'm going to get 2 pi on 6. That's pi on 3. So that means that if I add 2 pi on 6, well, now I'm going to get my next asymptote, and I better not put it too far away. I'm going to run out of room. So let's put it here. So pi on 6 plus 2 pi on 6 will be 3 pi on 6. So x equals 3 pi on 6, which is pi on 2. So I'll write equals 3 pi on 6. So that means that I've got another one going like this. And I'm going up to pi, so that's pi on 2 we've got to, so we can go further. So now I can say 3 pi on 6 plus 2 pi on 6. Well, that equals 5 pi on 6. Let's pop that one in. And, well, I don't have much more to go. If I add plus 2 pi on 6, well, that's going to equal 7 pi on 6. So my next asymptote is going to be 7 pi on 6. So I'll put it in there, but we're not going to go that far. So x equals 7 pi on 6. So that's how I found all my asymptotes. I'm just going to get rid of the bottom part so we can see more clearly. And you can see I've just added my period onto each of those. So now if I draw all of those in, now I need to consider where I'm going to cut it, and I'm going from 0 to pi. So obviously if I'm going from 0, I will cut off all that. So that can go. We don't need that side. So I'm going to be starting at 0, and it will go like this. So, and I can see already that that endpoint is 0, 0. So I'll put that in, and that means I don't need to find that. Now, let's have a look over on the right. So my complete cycle goes to 7 pi on 6, but I don't want to go to 7 pi on 6, I want to go to pi. So if I go from 5 pi on 6 to 7 pi on 6, well, I'm going to be going halfway of that, and it's going to be here to 6 pi on 6. So I can cut off everything from there. So along there. So let's get rid of this and get rid of this, and it will look like that. So now I know that this is pi and 0. And again, I'm not going to be using any formula to find my x-intercepts here, and this one is pretty easy. We haven't moved up or down. So the x-intercepts, well, we can say that our period is pi on 3. So if we're from each x-intercept, we haven't moved up or down, so it means that we can just plus pi on 3 each time. So 0 plus pi on 3 is pi on 3. You should put coordinates, not just the random point. Pi on 3 plus pi on 3 is 2 pi on 3. And, well, this would be 3 pi on 3, which is pi, so we'll just leave that like that. So we've considered the endpoints, we've got endpoints in, we've got the shape, we've got our asymptotes, and we've got our x-intercepts. So that would be how that looks. Let's move on to the next one, and no doubt it's going to be harder. Yes, indeed it is. So now we're going to be having a horizontal shift, and if you've been watching my videos on graphing, the Year 12 graphs, you will know that we move in the opposite direction for a horizontal shift. So look, let's address this. I'm going to first of all say y equals neg tan 2 x plus pi on 4. So this is important because if you do not take the 2 out, like so, you're going to have the wrong shift. You're not shifting by pi on 2 in the negative direction, you're shifting by pi on 4. So be careful, that will be a common mistake. So look, let's draw our basic tan graph, and this time, and I'm just going to do one cycle, I'm not going to do the horizontal shift yet. So the period equals pi divided by whatever's in front of the x, and in this case it's a 2. So across here means this is an interval of pi on 2, and that means that we have to share it. So this is x equals pi on 4, and this is x equals negative pi on 4. So our first cycle would look like this. And actually, I have not considered the negative. I might flip that now. So what I've drawn here is one cycle of y equals neg tan 2x. So I've not considered the horizontal shift yet, but that's what I'm about to do now. So let's do that. Let's draw the axes again, and now I've got to go in the negative direction by pi on 4. This pi on 4 is connected to the x. It is in brackets with the x, so that means we go in the opposite direction along the x-axis. So if I move everything by pi on 4, so that means I'm subtracting pi on 4 on each. This is 0, so I'm minusing pi on 4, minus pi on 4. So everything is minusing by pi on 4. So let's do that. This is going to be here, and it will look like this. So pi and 4 minus pi and 4 is 0. So this asymptote here becomes my y-axis. My x-intercept there becomes at negative pi and 4. I'll put the I'm going to put the coordinate in there, and then of course my other x asymptote there is going to be negative pi and 4 minus pi and 4 is negative 2 pi and 4 or negative pi and 2. So now I've got one cycle of that graph, and now I can consider the domain. So let's have a look. We're going from 0 to 2 pi. So in this case, I can now say, well, let's put another one here. We know that the period is pi on 2, so this must be x equals pi on 2. We've got another one, x equals pi on 2, so I'll put that there. So plus pi on 2 would be pi. Got another one, x will be 3 pi on 2. And the last one, 4 pi on 2. And that's 2 pi. So I've added pi on 2 for each because we know that the period is pi on 2. Now notice that we are going, let's double check that, domain. Yeah, from 0 to 2 pi. So well, this one is not going to be relevant because we're cutting it off. So I still like to draw it on the first cycle, and then then I can delete it if so needed. So let's put that there. Let's put that there. And we just keep repeating. And I believe that is all. Yes, there goes up to 2 pi. So it looks like we've got 4 complete cycles from 0 to 2 pi. So now the only thing we need is the x-intercepts. And I will pop them there. And we have not moved up or down. So if we have not moved up or down, it means we can just use the period to determine those x-intercepts. So over here, our x-intercept was negative pi on 4. So every x-intercept after that, we're just going to be adding our period, which is pi on 2, plus 2 pi on 4. So that would be pi on 2. So that's going to be negative pi on 4 plus 2 pi on 4 is going to be pi on 4. So pi on 4, 0, plus 2 pi on 4 would be 3 pi on 4. The next one, plus 2 pi on 4, 5 pi on 4. Plus 2 pi on 4 is 7 pi on 4. So now we have the x-intercepts, we have the asymptotes, we have considered the domain, and of course the endpoints are asymptotes. So that is our second example there, with a horizontal shift. Let's move to the last one. And this one actually looks pretty horrific for a couple of reasons. The first reason being that we see a really weird domain. It doesn't have a pi in it, and it doesn't look like, angle, like degrees either. The second reason it looks pretty horrific is because we've got this, a pi in our, to be considered when we do the period. And the third reason it looks horrific is because it's got a vertical shift. And when you have a vertical shift, your x-intercepts are a bit of a pain. So vertical shift makes x-intercepts harder. So look, let's do it. So I'm going to say the period equals pi, not 2 pi, because remember tan repeats after pi. Think back to the general solution. Remember we add on pi, not 2 pi. So pi divided by 2 pi, because what's in front of the x? 2 pi. So just because it's something weird, you don't just put the 2, you need everything that's in front of the x. So that means the period is 1 over 2. So it's a little bit nasty. When we draw this, we can say here is our asymptotes, and in between those asymptotes has to be the interval of half. So if it's an interval of half, this has to be x equals a quarter, and this has to be x equals negative a quarter. So I'm just going to draw that in. And that means that I have considered the period there. And of course, the amplitude is not going to change anything for us at this point because, well, we got asymptotes. So that means I've drawn y equals 3 tan 2 pi x. So 3 tan 2 pi x. And well, now I just need to consider that I've got a vertical shift of root 3. So look, I might just put that on now. So I'm just going to be moving up by pi on 3. So look, you don't want to draw this y equals root 3. I'm just putting it there so you can see what I've done. And let's use a different colour. So now I can say it's going to be like this. And my y-intercept there would be at root 3. So I've gone up by root 3. So 0, root 3 would be that point there. So look, now let's see the interval we've got. It's -7/8 to 7/8. So really it doesn't seem too nice. I'm just going to move this so I've got a little bit more room. And I might get rid of that as well, now that we've considered it. So look, let's see. This is a quarter, and we can say, well, a quarter is, our denominator there is 8, so I'm going to say it is 2/8. So then the period we said is half, and half with a denominator of 8 is 4 on 8. So putting a common denominator is quite nice. So that x asymptote is 2/8. So now we have to add 4/8. So that's going to be 6/8. So let's do that. 6/8. And if we write it nicely in terms of, like simplify it, our asymptote will be written as 3/4. So now we've got an asymptote of 3/4 there. Let's have a look. 3/4. We've still got a bit to go. 6/8, and we've got to get to 7/8. So I'm going to make a little bit more here and put another asymptote there, and I'd say plus 4/8. And 6 plus 4 is 10, so that would equal 10/8, and that would be 5 on 4. So x equals 5 on 4. And you see, that's too big. So we're not going to be having a complete cycle of the tan graph in that in this space here. So, we'll have just part of it. But this one we do. So look, let's put this in, and it's going to turn here. And then this one, well, from 3/4 to 5/4, or I should say 6/8 to 10/8, we want to get to 7/8. So 7/8 is very close to 6/8. So my guess is that it looks something like this. I don't think it's going to go over the x-intercept there. I don't think we're going to have it go up over the x-axis. So I feel it's going to be like this. And we'll find out when we find the x-intercepts. Because if we do find an x-intercept in the domain that works for that, then we would put it there. But for now, I'm going to take a bit of an estimate and say it doesn't. Let's go in the other direction. So now I've got x equals -1/4, so that is x equals -2/8, and now I am minusing 4/8, so minus 4/8, so that's going to be x equals -6/8, which of course is going to be x equals -3/4, so x equals -3/4. And then one more. Oh, I don't think I have much room there. I think this will be the last one though. And this will be -6/8 minus 4/8 is then -10/8, which is x equals -5 on 4. So now that we've done that, the working out I've done here with the denominator of 8, and that's really quite handy. But for the purpose of our graph, I'm just going to rub those out, because then, it's a bit messy. We don't want to see that. So I'll get rid of those. And now that you've seen how I've got all those x asymptotes, you don't need that. So look, now I'm going to, let's get the blue again. And now I can have a complete cycle here. There's my root 3. And then this one, well, here I've got, it's going from here. I don't think it's going to be reaching down past the x-axis. And this tells me that my asymptote here is superfluous, so not necessary, and my asymptote here is superfluous. So I'll get rid of those and I'll leave it like that. And look, I'm almost there. So it's actually looking pretty nice. I now need to find the x-intercepts, obviously, and the y, oh, no, we've got the y-intercept and the endpoint, sorry. So the y-intercept in this case, we could see that it's root 3, so no need to, do working out for that. Let's now go for the x-intercepts. So x-intercepts are when y equals 0. And you can see we've got 3 x-intercepts, but it could be that this goes over there and this goes here. So it could be 5 x-intercepts. In any case, I'm going to use my general solution, mainly because we've just done general solution, so it's nice to see how it applies to a graphing scenario. So let's do it. Y-intercept is when, x-intercept is when y equals 0, 3 tan 2 pi x. Plus root 3, yes. And by now you will be really good with solving for x-intercepts. So I'm going to say straight away, let z equal 2 pi x. Therefore, 3 tan z equals, actually I'll divide right away, negative root 3 on 3. So I've got tan z equals negative root 3 on 3. Negative root 3 on 3 is not in the table of exact values, but if we times by root 3 over root 3, well then obviously you are going to be able to get negative 3 on 3 root 3. So that means tan z equals negative 1 on root 3. So you see, that's really, really important that you can see how to obtain the 1 on root 3. Otherwise, you might not know that it's in the table of exact values. So let's draw it. And I have not put a table of exact values here, but tan of pi on 6 is 1 on root 3. So tan is positive in this quadrant, negative here, positive here, and negative here, because tan is sine over cos, and sine and cos are positive in quadrant 1, so positive divided by positive is positive, and negative in, sine is positive and cos is negative in quadrant 2, so tan is negative, and quadrant 4 also negative because your cos is positive and your sine is negative. So that's where we're going to be looking for our angles. So we've got negative tan value of 1 on root 3, and our angle is pi on 6. Now remember, from general solution, you do not need to do 2. And it's a little bit of a silly idea to do 2. It takes more work, especially when we're using something like this. So I'm just going to go for the easiest, which is this. And I can say z equals negative pi on 6. So it's negative pi on 6, and then I've got to say plus pi n. And I'll say pi n on 1. So notice it's not plus 2 pi n because, well, we want to go to the next tan. The next tan is here, remember? So if you add pi, you get to there. Add 2 pi, you get back to there. So you must make sure when you're using just one solution, one general solution for tan, you must say plus pi and not plus 2 pi n. Period of tan is pi. It repeats after pi, not 2 pi. So let's pop z back in, which is 2 pi x equals pi n on 1 minus pi on 6. And I'm going to divide by 2 pi. So x equals pi n on 2 pi minus pi over 12 pi. So let's see, we get, let's make a common denominator. Actually, no, let's cancel this first. Pi, and that will give us n over 2 minus 1 over 12. So, looking good, x equals 12 times 6 times 6. So that's 6n minus 1 on 12. So our general solution is 6n minus 1 on 12. And this is where you'll see it's just so nice, this maths, where we find our solutions, our x-intercepts. And we could have 20 x-intercepts. It would be so easy to find now that we have a general solution. So let's do it. So always start with 0. Oops. Neg 1 and 1. All right, let's see. I think that will be more than enough. So I'm expecting, so I look back at my picture there, I'm expecting 3 definite x-intercepts. I'm not sure whether I'm going to get x-intercepts here and here. So it could be 3, it could be 5. Let's see what happens. It could be 4, but I'm suspecting it's 3. I also should have looked at what my domain is, so negative 7/8 to 7/8. So let's write that down. So neg 7/8 to 7/8. And remember that if you're writing a general solution, n is an element of z because it's an integer. It has to be 1, 2, neg 1, neg 2, can't be a fraction. Okay, let's see, 0. So 6 times 0 is 0 minus 1, that's negative 1/12. That works. Negative 1, 6 times negative 1, negative 6, minus 1, negative 7/12. That works. Let's see, 6 times 1 is 6, minus 1 is 5/12. Yes. And negative 2. So we've got negative 12 minus 1 is negative 13 on 12. Well, that doesn't work because, well, that's minus negative 1 point something, minus negative 1 and a 12. So that's too small. What about 2? 6 times 2 is 12, minus 1 is 11/12. So I will have a look, and how I can see is I could put a common denominator here. So I could put it out of 24, 8, 16, 24, 7, 14, 21. So that's 21 over 24. So that would be my domain with a denominator of 24. Here, if I put 24 as a denominator, that's negative 2 over 24. Yes, and we knew that one was one of them anyway, but I'll pop it there. Next one, negative 7/12, so 24. So 2 times 12 is 24, 2 times 7 is 14. Yes, that one works. 5/12. Well, let's put a denominator of 24. 12 times 2 is 24. 5 times 2 is 10. 10/24. Yes, that works. Scroll down. And 11/12. So this will be out of 24 times 2, 21 over 24. And look, that actually is our limit there, isn't it? So, oh, oops, that was bit silly. 2 times 11 is not 21, obviously 22. So that's too big. So what this means is that the negatives no longer work, so I'm not going to sub in negative 3. The positive no longer works, so I'm not going to sub in positive 3 either. So I see I have 3 solutions. So actually I was quite right in my picture and in my estimate of where the endpoints would be. So let's put them on. Negative 1/12, negative 7/12 and 5/12. See if I can remember that. So this one would be negative 1/12. This one would be negative 7/12, I believe I had. Again, make sure they're coordinates. And the last one, oh, sorry, that would definitely not be negative 7/12. That would be negative 7/12. And I cannot remember. Let's have a look. 1/12, 5/12. So there would be 5/12. So they would be my x-intercepts. And again, notice how we used our, I guess we sort of really thought about, would we have x-intercepts here and here? I thought not, but then the algebra from solving for the x-intercepts showed me that I didn't either. I do need to find those endpoints though, and this is the last part. So we have endpoint where x is negative 7/8 and where x is 7/8. So let's do that. End point. So let's say the left endpoint. So x equals negative 7/8. Right, so our equation was y equals 3 tan, was it 2 pi x? Yes, it was, plus root 3. There we go. I just might double check that in case. Yes. So now all I need to do, I know that x is negative 7/8. I just need to sub that in. So y equals 3 times tan 2 pi times negative 7/8 plus root 3. And now we just do it like BODMAS. So y equals 3 times tan of 2 pi times 7 is going to be 14 pi on 8 plus root 3. All right, let's keep going. Y equals 3 times tan of negative 7 pi on 4 plus root 3. So now is the bit where it's that sort of BODMAS thing where you need to consider what comes first. And of course, we do the tan first. I'm going to draw a little picture. Actually, it's really important you draw the little picture. So pi on 4, tan of pi on 4 is 1. So you can look in the table of exact values. Well, you need to memorize it, but it's 1. And we have, it's negative. We're looking at the negative angle here. So we're going 7 pi's on 4 in the negative direction. So let's go. This would be the negative direction. This would be negative 4 pi on 4. This is negative 8 pi on 4. So negative 4 pi on 4, negative 8 pi on 4. So then we have it there, the stick is here. And we think, well, here is pi on 4 in there. And we know that the tan of pi on 4 equals 1. And tan is positive in this quadrant. So that means that this solution here is 1. This equals 1. So what we've got now is y equals 3 times 1 plus root 3. So that means y equals 3 plus root 3. So our endpoint there is negative 7/8, comma 3 plus root 3. I'm going to write it in straight away. So neg 7/8, 3 plus root 3. Okay, we need the other one, and in a lot of cases your endpoint y value will be the same, but in this one clearly it's not. So it's somewhere down there, and this is 7/8 for the x value. We need to sub in to find y. So let's do it. Same idea. Y equals 3 tan 2 pi x, which is now 7/8 plus root 3. So y equals 3 times tan of 14 pi on 8 plus root 3. And for the same reason, this is 7 pi on 4. So now, if I go 7 pi on 4, this is the positive direction. So here's 4 pi on 4, 8 pi on 4. So 4 pi on 4, 8 pi on 4, back 1. This is the stick. So our triangle looks like this. And you know this is a pi on 4 in here, and we know that tan is negative. So that means that, well, tan is negative 1. So y equals 3 times negative 1 plus root 3. Negative 3 plus root 3. So and this makes sense. Negative 3 plus root 3. Root 3 is between root 1 and root 4. So it's between 1 and 2. So negative 3 plus something in between 1 and 2 is still negative. Root 3 minus 3, so I'll put that in. And that's it. So we check we've got x-intercepts, yes. We've got our y-intercept. And we've got our endpoints and the shape of the graph. And also I should mention the asymptotes. So all those things would be important. And look, it's really important that you understand how to find the asymptotes and you understand how to find the x-intercepts and endpoints. So look, if you know some tricks for finding those, just maybe try the methods I've shown here before using the tricks, because you really want a good understanding. And that is all the examples.